Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Matias Castro-Tapia with us today. Hello, Matias. Matias.
Hi, Frank. Hi, Frank. How are you?
I'm doing awesome on this October 8th of 2025 as we record this. And so we are past equinox. And so let me ask Matias, what is your geolocation?
Well, I'm here in Montreal. I'm a PhD student at McGill University. So, yeah, just enjoying the last couple of days, like a bit warm
Okay,
because
so
the
we are
winter is
transitioning.
coming.
Yeah, we are
Yeah.
transitioning into fall, winter. Yes. Okay. Yep. Yep. Very good. And so you said you're a PhD student. When do you anticipate graduating?
Not sure, probably some point of 2027 I will
Okay,
be
cool.
graduating.
Cool. All right. Well, I will be among the first then to say congratulations, Dr. Castro Tapia.
Thank you.
It'd be an awesome thesis. Let's see. We are past equinox. I am in Phoenix, and we are definitely starting to cool down. So we are entering our fall phase. Although we still will get up into the 90F, so very quickly 33C or something like that. So yeah, but it's a dry heat. That's what we tell people anyway. So, uh,
Yeah.
but it's all good. Let's see. And Matthias, what do you like to do for research?
Yeah. I mostly focus on research on stellar astrophysics. I have done some research on red giant stars. Currently, I'm working on white dwarf stars.
Ah, cool.
Mostly, yeah. So we're gonna talk about it like
We are.
in a few minutes.
Very
Yeah,
cool.
but that's the main research I have been doing.
Very nice. Very nice. I predict an awesome thesis. So that is going to bring us, and that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one.
Yeah.
Three component phase separation for ultramassive white dwarf models. And Matthias, take us away.
Okay, thank you, Frank. So first of all, I'm gonna mention that I wrote this article with my current PhD supervisor, Andrew Cumming, who's an associate professor here at McGill University.
Great.
So,
Good job.
um, yeah. So, yeah. First of all, I'm gonna go through like a bit of a summary, like in the abstract. Like,
Okay.
we basically investigated the oxygen neon phase separation of ultramassive white dwarf stars.
Mhm.
So what motivates this investigation is basically in current stellar evolution codes, we only have like carbon oxygen and oxygen neons phase separation, but oxygen 16 neon 20 phase separation. But in ultramassive white dwarfs, we expect some other, we'll call it like impurities inside the composition of the white dwarf, which compose mostly about 15% of the core chemistry. So basically, we're trying to implement here extended phase separation up to three component, including these impurities that can be found in these ultramassive white dwarfs.
Cool.
So moving to the introduction,
Sure.
um, it is widely known that white dwarfs are mostly composed of carbon and oxygen, but this is mostly the case for less massive white dwarfs, which are usually with average mass of zero point 0.6 solar masses.
Yes.
But when we get to higher masses, like over 1.1 approximately solar masses,
Uh-huh.
during the previous stellar evolution phases, we drive carbon burning, which leads to a more oxygen neon enriched core. Yeah, but also we have these other species that are created during this carbon burning, which compose mostly, as I said, 15% of the core of the white dwarf, which is quite more. I mean, it's a bit more than in the case of impurities in the carbon oxygen white dwarfs, and it's a more varied mixture in this case of ultramassive white dwarfs.
Cool.
So, okay, going to the point of having phase transition in white dwarfs, because we we know now that there is evidence that white dwarfs can form a crystal lattice in the interior at some point of the crystallization. It's a
Mhm.
prediction from the phase diagram of these components, but we actually have some evidence of the crystallization in the cooling delays that we observe in the
Uh-huh.
HR diagrams of white dwarfs.
Very cool. Hmm.
So crystallization plays an important role in white dwarf evolution. It provides some extra heating from the phase transition. It provides also some buoyant, unstable regions, which are driven mostly because uh, when we form the crystal, most of the heavy elements, the heaviest elements are retained in the solid core,
Yes.
and we left behind a liquid region which is enriched now in lighter elements, which is makes it buoyantly unstable to the outer parts of the core of the white dwarf.
Cool. I'm
So
with you.
basically, we have these two key elements, and yeah. So as I mentioned, most stellar evolution codes that implement white dwarf cooling right now just only include the phase separation of carbon oxygen for the less massive white dwarfs
Yeah.
and oxygen 16 neon 20 for the more massive that can form um, this composition in these compositions in the core.
Okay.
So it is important to mention that I say explicitly neon 20 because in white dwarfs we also form neon 22, which is also present in carbon oxygen white dwarfs. But still in oxygen neon white dwarfs we have a huge amount of neon 22, and this portion of the neon 22 should separate with the neon 20 because the phase diagrams um, only depend on the fraction on the number fraction of the element and not in the mass fraction of the element. So
Yes.
all the isotopes uh, associated with one species will separate at the same rate with them.
Okay. Hmm. I'm with you.
Okay, so given said that, I'm gonna jump into section 2 to
Okay.
explain how we basically the idea of the paper was okay, we are going to construct some three component phase diagrams that can be used in ultramassive white dwarf mixtures, and
Cool.
we will implement this into the stellar evolution code MESA,
Okay.
since it only has this two component phase
Mhm.
separation, as I already mentioned.
Yes.
We construct a set of phase diagram based on four mixtures, which could be implemented like in oxygen neon white dwarfs, which is the main focus of the paper. So we have oxygen neon sodium, oxygen neon magnesium, but we also have some other phase diagrams which are carbon oxygen neons. Since I already mentioned in carbon oxygen white dwarf, we also have a portion of neon 22, which could have some important um, role in the cooling.
Yes.
And there is also like some prediction from mergers evolution, like if we have like a white dwarf and a giant that merge,
Yes.
they can form carbon oxygen and some huge amount of magnesium as the third most abundant element. So we constructed these four phase diagrams, but we only implemented the oxygen neon ones with
Okay.
the third element in this paper.
Okay.
Uh, and we show here the procedure of how implementing the how we constructed the phase diagram and how later implemented it, taking the carbon oxygen neon because it basically compounds like the three elements that are already implemented, like carbon oxygen or oxygen neon. So we can compare with the current implementation in MESA
Cool.
uh,
I'm with you.
or approach. So
Mhm.
if we go to figure one,
Figure one. Let's
show
slide down to figure one. Okay. Nice little GitHub address here, people. You can check that out. Okay. Ooh,
yeah.
here
So
we go. Phase
basically,
diagrams. There we go.
we use a method which is basically written in that GitHub code that uses the free energy minimization
Yes.
to search for the the mixture needed to minimize the free energy for a given density, temperature, and charges of the of the mixture that we had.
Okay. I'm with
So
you.
basically, here in figure one, we have like the phase diagram
Mhm.
for in the two first panel, we have the phase diagram for a given coupling parameter, this coupling parameter, uh, which is this gamma sub CM. It's
Uh-huh.
basically um, taking into account all these variables that I already mentioned, for example, density, temperature, and the charges of the mixture that we had that we have. In this case, we are showing two cases of the gamma parameter, which means that we have different temperatures. In this case, we can imagine that we are assuming that in the very interior of the white dwarf, we have a constant density, which is cooling. So
Okay.
basically, we are moving from uh, a phase diagram that applies first for the left jungle,
Yes.
then to the middle one.
Yes.
So for example, if we have a point um, with a certain composition, in this case, the compositions are given in number concentrations.
Yes.
So, and these diagrams, you can read it like it's basically a three-axis diagram,
Uh,
which is projected like in a triangle. So basically, um, the lines that are uh, kind of pointing towards the opposite side of each maybe not the opposite side, but if you look at the ticks of the figure, you can
uh,
see the direction of where the the compositions are basically pointing.
I'm with you.
So if you are in certain point of the diagram in the liquid phase, which is all that is below visually the green line,
Yes.
you will start cooling, and at some point you will reach this green line,
Yes.
which is the liquidus line, which is like the limit for having a liquid mixture. And we will fall into this region where we have these different lines, this I don't know, the colored lines, which are the unstable region
Yes.
where we're transitioning from liquid to the solid.
Uh-huh.
Um, Basically, the mixture doesn't last too much time inside this um,
Transition region.
the transition region, the unstable region, because once we form the solid, they quickly sediment towards towards the center. And also in white dwarfs, we can assume that this transition is mostly uh, at a constant temperature. So basically, we will form a mixture that now have a different composition in the solid and in the liquid.
Okay.
So this is like the kind of the big picture of the phase separation inside white dwarfs.
Mm-hmm.
In the last triangle, we show the liquidus line evolving over different gamma parameters. So the gamma parameter is,
Ah,
which is the coupling parameter, is inversely, sorry, is proportional to 1 over temperature. So
mm,
basically, a higher coupling parameter is lower temperature. So we see the liquidus line moving from certain mixture towards the other end of the triangle, like moving towards carbon-rich mixtures.
uh-huh.
And this means that for certain mixture, uh, we have a specific value of the gamma parameter in which we will transition from liquid to solid. If you
Okay.
see none of these lines intersect each other, this means that in the liquid phase, we cannot have like liquid-liquid separation like it happens, for example, when we have like oil mixed with water, we have like this
Yes.
liquid-liquid separation. In
Yes.
this case, the liquid state is it, it is stable until we reach the freezing line. So basically,
Right.
we can write
Mhm.
a function which describes if we have certain composition and we are at the freezing point, we can transition from one
Phase.
from one phase to another,
Uh-huh.
uh, just depending on the on the local composition that we have. So basically, if we go to figure 2 to explain this in a much better way.
Cool. I'm with you. Okay. Let's slide on down to figure 2. Okay, here we go.
Yeah.
Okay.
So we will look first at the right panel
Okay.
because it's the way how the phase separation of two components is implemented in MESA.
Okay.
Uh, we have the dashed lines, which are the Bloom and Delacote diagrams. Basically, we are writing here in terms of the
Uh-huh.
abundance on the oxygen for the upper panel. We have certain difference in between the solidus and the liquidus.
Uh-huh.
So basically, this is just a function um,
Right.
of the oxygen mixture. Basically, these oxygen mixtures in the liquidus are just saying that we are at the freezing point. So at the freezing point, we
Right.
will have this difference in the composition between solid and liquid.
Cool.
Um,
With you. Mm-hmm. I'm with you.
so currently in MESA, we can actually follow the freezing point because in the equation of state is implemented a phase. It is implemented a phase parameter which shows you where in the start you are freezing or you are in the liquid state. So
Yes.
basically, by following that, we can only take the freezing point, look at the composition, and make the fractionation of the elements, basically putting some quantity of certain element in the solid and certain quantity in the liquid.
Okay.
But this is we are first looking in the right panels for the two components mixture. So
Mm-hmm.
basically, it only depends in one component because we have like um, conservation of number of particles and also conservation of mass. So
Yes.
basically, the other abundance will be one minus the one shown in the,
Yes.
yeah,
Cool.
like in the lower panel, the right.
I'm with you.
But in this case, since we have three components, now we need two independent variables,
Yes.
which in this case of the left hand panel, we
Okay.
have for example carbon and oxygen,
Okay.
and we are showing in the triangle, which is basically in the lower side,
Uh-huh.
which is in blue scale, we're
Yeah.
showing the delta XC, which is basically the difference in the solid and the liquid for the carbon.
Mm.
And we also need a function for the oxygen. This is for the phase diagram of carbon, oxygen, neon. So
Okay.
basically, if we now go to equations
Okay.
1, 2, and 3,
Okay. Let's slide down to 1, 2, and 3. Here we go.
yeah. So the procedure is the following. We have these number concentrations. We have to change to mass concentrations because or mass abundances, because in Mesa that's the way we handle the um, the chemical abundances.
Uh-huh.
But basically we now have two functions that depends on two independent variables. So basically we are computing these delta x's,
Okay.
1 and 2, this time in terms of the mass abundance, because we have to do that for the implementation.
Okay.
And for the third element, using mass conservation, we will have that the change in the concentration will be given by the output of these two functions.
That makes sense.
So yeah, so this is kind of following the implementation of Evan Bauer, who first implemented this in Mesa for two components, but now with three components, we need like a higher number of independent variables and
Yes.
plus one another function for the deltas.
Very cool. Good.
So
Good shout out.
yeah, yeah. So basically, in summary, for the implementation, we take the phase diagram, we construct tables for certain. If we have three components for x1, x2, we will have certain delta x1 and delta x2.
Yes.
And then you can derive the abundance of x3 from mass conservation and the difference on x3 when the elements fractionate using delta x1 and delta x2.
Cool. I'm with you.
So
All right. Very good.
computationally in Mesa, uh, we read the tables and we do an interpolation with a function that do 2D interpolations in Mesa. So basically we read the compositions, look into the tables, look at the deltas, and then update the mass fractions into the code.
Very good. I'm with you. Mm-hmm. Good.
Yeah.
Okay, cool.
Okay, I think that summarizes most of the implementation. I
Yeah.
think people are interested can go into the details of this, reading that part. But I would like to speak now about the application to actual white dwarf models, which is
Uh-huh.
section 3.
Yes.
So in section 3, we basically construct some oxygen-neon ultramassive white dwarfs, which contains some of these impurities in their cores.
Mm-hmm.
And we implemented this three components phase separation that we already explained into these models and compared with the models with only two species.
Okay. Makes sense.
Okay, okay, so I'm going to explain this now in figure 3.
Okay, let's slide down to figure 3 composition profiles. Okay.
Yeah, now here we have the composition profiles of a oxygen neon white dwarf whose third most abundant element is sodium 23.
Okay.
So we here are basically showing three cases of the phase separation implementation. the solid lines are basically oxygen neon sodium separation, 3 components, and we have included into the neon
Okay.
the neon 22, which is also present in the white dwarf core, as we can see with the color code here, the
Yes. Uh-huh.
abundances.
Color code here.
We compare in the Dutch lines, we use the 2 components phase separation, but now including the neon 22.
Okay.
And in the dotted lines, we use the current phase separation implementation, which is basically oxygen, but neon only with the isotope 20.
Right. Okay. I'm with you. Mm-hmm.
So to summarize a bit more the figure, we have the composition profile inside the white dwarf. The x-axis is the mass coordinate, so basically indicates the mass. Is the sorry, is the mass coordinate. So basically,
Mm-hmm.
it shows the fraction of the mass that we are looking at inside the white dwarf
Right.
until the surface, which is 1, basically.
Right. Yep.
Um,
Huh?
we are seeing in the y-axis the mass fraction of the elements. In the upper panels, we are seeing all the most abundant elements inside the white dwarf,
Okay.
which are basically 6. Um, and we see the evolution in time as the crystal core grows. For example, here, the shaded area is basically the area that has already crystallized. So basically, we
Okay.
are going from bit, a bit like 20% of the core crystallized to 90% of the core
50
crystallized.
here and
So
roughly 90 here. Yes, I'm with you. Uh-huh.
yeah, so we
Okay.
see, and also we zoom in into the oxygen neon composition in the lower panels
Yes.
to see the main takeout of this figure. So we see that for the cases of the 3 components phase separation,
Okay.
we see that the mixing induced by 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 adding more components into the phase separation
Yeah.
is is bigger than the case of the oxygen neon, the simplest case of the oxygen neon. We can see that because uh, we see that the composition profiles in the liquid phase now are flatter over time. So basically, when we induce this buoyant unstable region that I explained at the beginning,
Got it.
we are inducing a composition gradient which is larger, which produces more mixing over time.
Yeah.
And we can see that, for example, for the Dutch line with the oxygen neon, including neon 22, we
Uh-huh.
can almost match the 3 components for this kind of extra mixing induced by the
Mostly.
by the new phase separation. So
Uh-huh.
basically, this is saying that we not only have to consider like this thermos abundant element, but also the other isotopes that are separating with the other abundant elements in the core.
I'm with you.
Uh,
Cool. Very nice.
yeah.
Good.
Okay, so how this actually translate into some kind of physics that we can apply in the models more than this extra mixing that we see in
Yes.
section 3.1,
Uh-huh.
no, sorry, 3.2, we use mixing length theory to uh,
Get there. 3 point.
calculate. Yeah,
I'm with you.
I think it's before the figure.
Yeah, I'm
It's
I'm
just
bopping around here a little bit. Okay.
yes, yes, yeah. It's
I'll
just
find
a
it. Here we
type.
go.
Yeah,
Hidden on this
yeah,
page 5. Here we go.
yeah. So basically here we use mixing length theory. So if we now jump to equation 9,
Equation 9. And there we go. Yes. Okay.
Yeah. So in mixed length theory, we aim to describe the buoyantly unstable region. So basically, the buoyancy acceleration will be proportional to the density contrast induced by this phase separation. So basically, okay, just to remind this, we have formed a solid lattice, and this solid lattice is enriched in heavy elements, uh, to say, and we left a liquid region outside this solid region, which is enriched in lighter elements. So
Yes.
basically, this new region will be buoyantly unstable compared to the rest of the background of the white dwarf. So
Okay.
how we compute this buoyant acceleration, basically we take the density contrast, which depends on the gradients on the temperature and on the composition.
Yes.
Basically, we are just expanding into like the equation of state,
Uh,
considering that the pressure
yeah.
remain balanced because convection, which is the um, the, the buoyancy that is happening here,
Yes.
is transported at a velocity which is less than the sound speed. So
Mhm.
basically, we
Okay.
can assume that we are a pressure balance.
Good. Okay.
So in this approach, which I am not going to explain in detail because it's in another paper, which is this Castro-Tapia et al. 2024A, we
Mm.
explain in more detail the details of basically the mixing length.
Uh-huh.
But the idea here is just from equation 9, convert these gradients into fluxes, like flux of heat and flux of elements. So if we go now to, sorry,
Uh-huh.
equation 12.
Yes, there's our flux. And equation 12. You get
Yeah,
this
okay.
basically
So
composition and flux.
could you go a bit up to see 12 and 14 at the same time?
12 and 14 at the same time. There we go.
Yeah, so in equation 12, we have written a form
Mm.
of the total composition gradient that can be computed from the fluxes, which are these Fxi.
Yes.
So each flux of elements, which can be computed from the difference that we have when fractionating the elements, translate into a gradient.
Okay.
And for an equation 14, we have this delta rad, which basically defines the whole uh, heat flux that we have, which can be expressed in terms of the luminosity, for example.
Yeah.
Um, so having said that,
Cool.
we see in equation 15 now how the density contrast changes based on these two new introduced variables for expressing this in terms of the fluxes.
Very cool. Okay.
So
Very good.
the total heat flux is obtained basically from the local luminosity that we have,
Yes.
and the composition flux in this case, which will mainly will drive the instability, is computed from each flux of the elements, like transiting from the previous liquid state to the new liquid state. So before we have a liquid background which is stable, then we fractionate the elements, we put some heavy elements in the core,
Yes.
we left this zone now with lighter elements, we compute the difference between these two, the previous one and the new one, and
Yes.
we compute the fluxes and put this into the density contrast.
Very
So
cool.
basically, for the case of the heat flux, it is mostly a constant. We can mostly consider this a constant value here. So as we did in Castro-Tapia 2024, we see that that the buoyant instability in this case is mostly modulated by this tau parameter, which depends on all the fluxes.
Yes.
Oh,
Yeah.
I think we are not seeing the tau
Got any questions?
equation 13, I
Oh,
think,
13. No, yeah,
because
13.
from 12 to 13, basically, we
Hmm.
have now in a more explicit form tau, which depends on all the fluxes of each element. So
Okay.
basically, what we saw in this Castro-Tapia et al. And also in other paper in 2023, which is Fuentes et al., I think. Yeah.
Mhm.
We see that for tau, in this case, larger than 1, we have a regime of overturning convection, which is a convection which occurs almost in an adiabatic regime,
Okay.
and it is fast, like uh, it's faster than the I mean, if you compare the time scale for convection and the time scale
Yes.
uh, for thermal diffusion, we
Yeah.
see that basically convection is faster than thermal diffusion.
Yes. Okay.
And this is one regime which occurs mostly at the beginning of the crystallization when we have a very small core. So we have a huge flux of elements. But then, since thermal diffusion is very efficient in white dwarfs, basically given by the electron conductivity,
Yes.
um, we fall into a regime which is inefficient. So the convective motion is lower than the thermal diffusion. So the convective velocity is reduced by the effective thermal diffusivity.
Cool.
Uh,
I'm with you.
so if we go now to figure 6.
Okay. 13, 14, 15. I'm with you. Okay. Now we slide down to figure 6, buoyancy fluxes. Okay.
Yeah, so I'm gonna focus on the upper panels
Okay.
first.
Mm-hmm.
So we here computed the buoyancy fluxes, or the flux that mostly modulate the buoyant instability in this case, which is tau, this tau parameter. And
Yes.
we see that including more species into the phase separation boost the density contrast,
Mm.
which is expected. But we also see that those species that are neutron rich,
Okay.
by neutron rich, I refer to those species that have more neutron than protons,
Uh-huh. Yeah.
uh, have a higher effect on the buoyancy flux.
Interesting.
Uh, for
Mm.
example, uh, we know that neon 22 and sodium 23 have more neutrons than protons, and we see in the upper panels that the buoyancy flux is affected like uh, mostly in an equal way if we add only neon 22 and then we add the other element, which is sodium 23.
Right. Yeah.
But in the case, for example, in the lower panels, we use white dwarfs with oxygen, neon, magnesium 24 compositions, and magnesium 24 has equal numbers of neutrons and protons, and the effect on the buoyancy flux is not uh, too big when compared with the effect of only adding the neon 22. If we see the addition of only neon 22 can almost match the effect on of adding the third element.
Cool. Very cool. And we got some pink lines here, which are, I guess, differentiating tau greater than less than 1. Yeah. The pink.
Yeah, I think another point here is the fact that, as I mentioned before, we have efficient convection at the very beginning of crystallization for a short time,
Mm-hmm.
but now we have for a longer time, we have this efficient convection, which is when we have tau larger than 1, which
Okay.
is, we can see by looking at this pink line where I mark tau equal 1.
Qualities.
So,
Okay. Cool.
uh, okay, so this is one thing. this tell us about what we saw before in the composition profiles about the mixing. If we have a buoyant stable region which is more efficient, we will have more mixing.
Yes.
But also this can be applied to another theory, which is basically if this buoyant stable region can generate a magnetic field at some point.
Uh,
Uh,
yeah, yeah.
okay,
Okay.
so there is a theory that if we have efficient convection driven by this composition gradient,
Yes.
combined with the rotation of
Ah,
the white dwarf, we can drive a magnetic field.
yep.
So for driving this magnetic field, in previous work, we have shown that we need this efficient regime. So having this efficient regime for longer could favor this scenario.
Yes. Cool.
So that's one another implication of on this
Yes.
uh,
Yes, yes, yes. Okay. Nice.
on this implementation. So now
I'm with you.
I'm gonna talk about the cooling delay, which is section 3.3, but we can just look at figure 7.
Okay, figure 3, 7. Cooling curves.
Okay, yeah. So another implication for white dwarf models using this new implementation of the phase separation
Right.
is the cooling delay.
No.
So basically, in Mesa, there is already a way to compute the heating driven by the composition differences during phase separation.
Okay.
So we only uh, implemented the phase separation routine, the new extended phase separation routine, and see what happened um, to the cooling curves. So
Right.
basically, we are seeing the luminosity and the cooling age of the white dwarf, which is by cooling age I refer to the age that
Wow.
um, the
Mm-hmm.
age of the white dwarf since the formation of the white dwarf itself. So
Yes.
basically, we have the three cases of phase separation compared also with the case of no phase separation at all.
Right. In both.
Um,
Mhm.
so we have the two components that is already implemented, Oxygen 16, Neon 20. We have the two components, but now including Neon 22, and the three components, including the third most abundant element for two different cases of the core composition.
Yeah.
Uh,
Okay. Mm-hmm.
so we see that the cooling curves become different when adding more elements to
Okay.
the mixture.
Okay.
Specifically in the oxygen neon sodium case, we see that not having phase separation and having phase separation just produce a very small delay in the cooling,
Yep.
but when adding the other elements, it is boosted.
Yeah.
Now, if we go to equation 8, we actually computed the
Equation.
amount of, no, sorry, figure 8.
Figure 8. Okay. I'm
Yeah,
with
yeah,
you. Okay. Let me do. Okay. Good. Good. And figure 8. I'm with you. And the
yeah.
cooling delays. Yay. Here we go.
Yeah, so we computed the actual cooling delay we observe in the model. So we take the luminosity for the model without phase separation, and at a fixed luminosity,
Yes.
we computed the cooling time at which the white dwarf is for the different models. So in this
Yes.
way, we can compute the cooling delay that we are observing at certain luminosity if we want to compare with observations, for example.
I'm with you.
Uh,
I'm
we
glad.
see that for the oxygen neon sodium core, um, for the two species, oxygen 16 neon 20, the
Yeah.
cooling delay is about 0.05 gigayears only, but by
Yeah.
including the whole new extension of the phase separation, the new delay is about zero point 0.4
Wow.
gigayears, which
It
is
is.
almost like 10 times larger
Wow.
than the case with having the current implementation in Mesa of the phase separation.
Wow.
Uh, Yeah, and for the case of the neon oxygen magnesium core, we
Yes.
see that the cooling delay is almost 3 times
Uh,
the delay that we have with the current implementation.
dash lines.
Okay.
I'm with you. Uh-huh. Uh-huh. Wow.
Yes,
Not
that's
true.
the second. Yeah, that's the second implication that we have for white dwarf models, and we discuss last one in section 3.4.
Okay. Section, let's go up to 3.4, 3.3, there's figure 7, and 3.4, implications for pulsating models. Ooh. Okay.
Yeah, so nowadays we have some information of some white dwarfs that show variability, which are a sign of pulsations inside the white dwarf.
Uh-huh.
And there is a specific kind of pulsation, which are the gravity modes, which are basically driven uh, by a displacement of the fluid inside, but this fluid keeps oscillating instead of growing into a whole instability. So basically, we move a bit the fluid, and we have a restoring force, which will be the buoyancy, which
Yes.
push the fluid out, and then we have the gravity, which is pushing the fluid towards the core again.
Cool.
So basically, these pulsations are modulated by the same criteria as convection. It's basically the Brown-Weisala frequency
Yes.
in short term, um, uh, which basically, as we saw before, if we have certain value of these gradients, we have an unstable region. But in the case where it's stable, if we perturbate the fluid, we will have these oscillations that will translate into variability of all the stellar properties that we see.
Very cool. I'm with
So
hmm
if we computed these Brown-Weisala frequencies from the code,
Okay.
uh, using the current implementation of phase separation and the new implementation, and in figure 9,
Yeah, let's slide down to figure 9. Here we go.
we
BV.
showed these Brown-Weisala frequencies.
Uh-huh.
So basically, as I said, these gravity modes are mostly modulated by this Brown-Weisala frequency.
Yes.
So we see that due to the extra mixing induced by adding more components to the phase separation, we see that the composition part now is more flat, which
Yes.
means that in equation 17, this Nabla is smaller,
Right.
so the frequency of
Okay. Mhm.
the Brahma-Sala frequency will be smaller in this region.
Yes.
This means that in this region, which is now more mixed than before, the gravity modes will propagate slower than before.
Okay.
And for example, if we look at the middle panel, where we have about 80% of the core crystallized, we
Yeah.
have a new uh, coordinate system here, but it is 80% of the core I mentioned in the text somewhere.
Yeah, you
We
got
see that,
yeah, I'm with you. I understand this axis, yes.
yeah,
It's a goofy one,
yes,
but yes.
yeah, but I explained in the text that it's 80% of the core, the middle one.
Yes.
We see that in the blue line that we have a smaller frequency
Uh-huh.
um, just outside the core, which is obviously a main effect of the mixing. This means, and also this in this part of the star, uh, we have the smallest Brown-Weisala frequency. If we look
Uh-huh.
more outside of the star, is the frequency keeps growing, which
hmm
means that the waves sorry, the gravity moves propagates slower in this region, which can lead to a conclusion. For example, if we use the current model for oxygen neon phase separation with only two species,
Yes.
we could uh,
Uh-huh.
we could predict a crystallized core
Period.
which is uh, which is
Yeah.
larger in size
Yeah.
than in the case that
Cool.
we have the three components phase separation.
Uh-huh.
That's why in the crystal core the gravity modes doesn't propagate. Then you don't see the modes they're propagating. And then okay, let me think a bit more about it. If we have like the smaller frequency just outside the core, it means if we just don't see for enough time like the variability, we miss this part where the waves propagate slower. So basically, if we, in summary,
Right.
the predictions for the size of the crystallized core can be wrong if we use the oxygen neon phase separation with only two components. We need more components to have a better prediction of the core. And also there is a paper that cited this one
Always
in
good.
which in which they use different composition uh, for I mean it is a standard way to use different composition models for the white dwarfs
Yes.
to characterize the pulsations.
Uh-huh.
So points this new implementation points towards a more accurate predictions of not only of the crystallized core but also of the composition of the white dwarf,
Right. Right.
the story and the story and the evolution of the order itself.
Very nice. Cool.
So yeah, that's the last implication we discussed. Uh,
Cool.
I think we can go to the conclusions now.
Sure. Okay.
Summary and discussion, basically.
Yeah, where are we here? Somewhere around here. Summary and discussion. Yep.
Yeah, so in summary, again, we took uh, a tool that was developed before based on the free energy minimization to construct phase diagram of three components.
Yes.
We implement those phase diagram in the oxygen neon white dwarf models, which has mostly oxygen neon, but around 15% of the core composition is other elements uh, other than oxygen 16 and neon 20.
Yes.
And we see that including this new including the phase separation of three elements into the stellar evolution code, and also including the isotope of neon 22, which wasn't considered before,
Yes.
uh, even when it should separate with the neon 20, has an effect on the evolution of the white dwarf. It has effects on the mixing, on the buoyancy induced by the fractionation of the element.
Uh-huh.
It has an effect on the cooling of the white dwarf, and we saw in the last uh, section subsection of section 3 that it affects the possible predictions for pulsating white dwarfs,
Yep.
basically because we are trying to constrain the core composition and also the size of the crystallized core, because it will tell us about the whole evolution of the white dwarf.
Very.
Uh, I discuss a bit further here about this major problem in white dwarfs, which is like the multi-gigayear cooling delay in
Uh-huh.
ultramassive white dwarfs.
Right.
The cooling delay that we predict here is not comparable to that because it is quite smaller. The multi-gigayear cooling delay is about more than 1 gigayear delay.
Uh-huh.
So we are below at least below one order of magnitude.
Right.
But this multi-year cooling delay the theory that best predict this multi-layer cooling delay is actually related to phase separation in three components,
Yes.
which is the neon 22 distillation in carbon oxygen white dwarfs.
Mhm.
So we discuss a bit in the appendix that this implementation in Mesa can be of the phase diagrams can be applied to this case in the future. We haven't developed the yet the code to implement this distillation process, which is basically
Right.
when we have uh, the crystallization, we form some crystals that are not heavier than the liquid background, but
Good.
they are lighter and they will float up
Yeah.
and will mix at some point.
Yep. Cool.
So we discussed at some point in the appendix that we can use this kind of implementation of the phase diagrams in Appendix B, I think,
Yep.
for that case, but we still need the actual implementation of the crystal floating and mixing in the uh, in the code itself.
Very,
But it has some promising uh, future applications.
very.
Yeah, I think yeah, that's mostly the paper. I think I could mention in Appendix A, yeah, that in Appendix B we compare with a previous work by Simon Blouin,
Right.
uh, who computed also phase diagrams of three components.
Yes.
And we need this delta X neon to be negative to have distillation. So basically, in our work, we have that regime for certain values of the gamma parameter. So we can, at some point, implement this
Yeah.
distillation with the phase
Cool.
diagram we put in Mesa.
Very cool. Okay.
Yeah,
And appendix
just
A, here's a
yeah,
solid core correction.
one yeah one last thing I should mention is that in Mesa there was like we could say uh, an error on the implementation of the following of the core. So basically, what happens is that in numerical simulations,
Yeah,
we
yeah.
have to deal with discrete models. We don't have a continuous model everywhere. So basically, for implementing the phase separation, we have to separate into cells uh, of that contain certain mass of the star,
Okay.
and we put some of the fraction of the elements in one side and one fraction of the element in the other side, and
Yep.
we compute the energy taking the difference in the energy we have initially and then when we fractionate. And this produces uh, extra heating, which
Yes.
is physically expected. But since we have these discrete models, we are putting some energy into the cell, which contains the core at some point, and this will kind of melt the core.
Or
But this is an artificial effect of the discrete model because as I
yes.
mentioned before, when we separate this crystal will sediment into the core, but we cannot like put in a very accurate way when we had these discrete models uh, that process happening.
Right.
So in the current implementation of Mesa, the follow the crystal core at some point will melt the core and will update the core mass if we don't have the first cell I mean, not the first cell, but the core cell
Yeah.
in a crystal phase.
Uh-huh.
It will update the core, putting the cell into zero. Uh, uh, I
Cool.
mean the size of the crystal core to be zero, and that will melt the the core. But since the implementation of phase separation only goes in one direction from liquid to solid, we will have this discrepancy when transiting to solid again if we are melting the core. So basically,
Yes. Yes. Okay. Uh-huh.
yeah, so basically we stated in the code that if we already have a core which is larger than zero, then we don't expect that to decrease
Right.
and become zero again. Just it will continue growing. So that fixes this issue. That, for example, in figure 10 in the lower panel, we see that the oxygen profiles, for example, when melting the core is pushing more oxygen pushing more oxygen towards the liquid and less uh, uh, and less oxygen towards the core, because we are melting. We
Right.
are not fractionating when melting, but then we are crystallizing again. So we are taking again oxygen from the core and putting into the liquid, which is an artificial artifact, basically, due to this problem. But we fixed that, as I said, just stating that the core continues growing as the cooling advances.
Okay. Very good.
Yeah.
Cool. I'm with you. I think that wraps.
Yeah, so yeah, I think that's the main of the paper, is just how
Uh-huh.
we can improve stellar evolution models for white dwarfs, having this implementation of the three species phase diagram.
Very cool. Very cool. Matias, beautiful work. Beautiful work. And I want to thank you so much for walking us through your very awesome article.
Yeah, thank you so much for the invitation.
Sure. And you kind of mentioned it a couple of times, or at least potential directions. And so let me push on it a little bit more. And where do you think we go from here, given the published article? At some point, you said the word observations. At some point, maybe you want to put these up against the observations, particularly the astroseismology, the pulsational results of older white dwarfs. Put it up against some of the cooling curves of observations. And as you mentioned, there's still some additional theoretical work to do and then the implementation of it. So where do you think we go from here in the near term? Or at least on the time scale of your thesis?
Yeah, I think that one natural thing to do next is take these already done models for pulsations that people have done and try to see how the prediction that they make for the size of the crystal core and the composition of the white dwarf changes with these new models that implement the three components phase separation.
Cool.
Also look at the cooling curves of current models. As I said, it doesn't reproduce the multi-gigayear cooling delay, but it will somehow correct some of the cooling
Uh-huh. Uh-huh.
as we have more cooling induced by this three component phase separation.
Right.
At some point, I think more in the far future, we expect to implement like more complex phase diagram. I think that
Ooh,
the ideal case for white dwarfs will be like at least a five components.
there you go. I was gonna say, if three is good, 4 or 5 must be better.
Yeah, as we saw in one of the figures, the main of the core, the main composition of the core is up to five.
For
I
a,
mean, 99% of the core will be five species.
sure, sure. And the star that was born probably had some iron in it, and that iron hangs out all the way to the white dwarf.
Mhm.
So yeah, it might be interesting to include iron in that, and see what you get.
Yeah, yeah,
Very
yeah,
cool. Very cool.
yeah,
It'll be really exciting to see this develop over the next couple of years. It'll be really cool. Very nice.
yeah. It's,
Awesome. All right, Matthias, thank you once again for walking us through your very awesome article.
yeah. Thank you again for the invitation and have a good day.
Sure. And I hope that made your astronomy day just a little bit better, everyone. And we will see you on the next one. Bye bye.